Hey guys, in this video we're going to go over different alpha, beta and gamma radiation and the different ways of detecting them and how we use these to figure out what type of radiation was present in the source. Okay, so the first type is called an ionization chamber. So what an ionization chamber is that we basically have an ammeter here, and the ammeter is going to detect the current. Okay, we're going to have our source of radiation. So again, we've got some unknown source of radiation. We don't know if it's alpha, beta, or gamma radiation. And if you need a quick recap on what alpha, beta, and gamma radiation is, just go see our earlier videos about stable and unstable nuclei. So we've got a source here, and we don't know if there's alpha, beta, or gamma inside it. So what happens is that source of radiation, there's going to be some air in here. And that air, when it meets the radiation, is going to get ionized. And we know when air gets ionized, we're going to get those negatively charged particles and the positively charged particles formed. Okay. Here you can see there's my positive side of my cell, so it's going to be my positive plate. And there's my negative side of my cell, so it's going to be my negative plate. So what happens then is my positive ions get attracted towards the negative plate, and my negative ions get attracted to my positive plate. And you see what happens then is we get a complete circuit, and we're going to get a current detected then on our ammeter. The current we detect on our ammeter is going to be directly proportional to the number of ions created per second. So if we have a really high current, what that means is we're getting loads of ions created per second, and what's going to happen there is get a high current flowing. And the one that we get that's going to give us the most ions per second is clearly our alpha particle. So if we get a really high current, we know it's because of our alpha radiation, because it is the most ionizing. Okay. The next then is beta, and the next one is gamma. And remember, the reason alpha is the most ionizing is because it's got the most charge, right? It's the largest particle, remember, because it's a helium nucleus. So it's the most ionizing. It creates the most number of ions per millimeter. However, one to be aware of here, alpha particle, even though it's the most ionizing, it creates the most number of ions per millimeter. The problem then is it's got the shortest range. And its range is roughly around 5 centimeters in air. So if this source, it gets moved greater than 5 centimeters away from our chamber, we're not going to detect any current at all, even though it contained alpha. So yeah, our source might contain alpha. It might be the most ionizing. We might get zero current, which might make us think that there isn't any alpha there. So you have to look at the distance to see how far away the source is from our chamber. Okay. The other one here is called a cloud chamber. Cloud chamber kind of works like the same with airplanes. You know, see airplanes, you see the path in the sky? So cloud chambers, what they are, is inside this chamber here, we're going to have air that's all vapor. And that vapor is supersaturated. We don't even know what that is, but all it means is that the vapor is all ready to condense, right? It's ready to change from a gas to liquid, but it needs something to basically just spark it to happen. So what happens is, if we have any type of source of radiation, what's going to happen is it's going to cause ionization. So it's going to cause ionization, and when it causes ionization, it causes that vapor to condense to form a droplet, and that droplet then forms a path that we can see. And hopefully you can see there's two different paths here. We have our thicker lines that are always a bit shorter. So the thicker lines are because of alpha. And the thicker lines are because alpha is a heavier particle, and it is the most ionizing. So again, we can see the path of alpha is always shorter than those other squiggly lines. There's two different paths of alpha. So we have the longer lines and the shorter lines. So what we're saying here is there's two different types of alpha. We have one with more kinetic energy, so it gets further, and one with less kinetic energy. But again, those thicker lines are because of alpha, because it's heavier, it's the most ionizing, and it has the shortest range, which is why they're really short lines. Okay? The thinner lines then are because of our beta. So the thinner lines are because of our beta. So beta ionization. So the thinner lines because of beta, because beta, again, is a smaller particle and it's less ionizing, which is why they can travel much further. Okay, so we can use a cloud chamber to see what type of path we detect. So we get those thick, short lines, we know it's alpha, and we get those longer, kind of squiggly, thin lines, we know it's beta because it's less ionizing and it's got a longer range. Okay, the last one then is our Geiger chip. So Geiger chip, you probably heard about in your GCSEs. A Geiger chip, again, is a way to measure radiation. So what happens is we have radiation coming in here, and we want to figure out, is it alpha, beta, or gamma radiation coming in? So we're trying to figure out what is in our source, okay? So hopefully you can see here, again, we've got our negative side of our cell. So our negative is the container there of my Geiger chip, and the positive here is going to be that thing in the middle So like a rod in the middle of the Geiger tube. Okay, so again, what happens is, let's say we have our radiation comes into the Geiger tube. What's going to happen is going to ionize that air inside that Geiger tube. And again, we're going to get our negative ions and our positive ions. What's going to happen then is their negative ions move towards that positive plate, and the positive ions move towards the negative container. Then what happens is we're going to get a pulse of charge that travels around our circuit, and the counter records that charge. Okay, so the counter is we're going to record that charge that goes through. So basically, the more ionization, that means the more charges are going through, so the more counts are recorded in our Geiger tube. Okay. One thing to be aware of Geiger tube is a thing called dead time. Okay, so sometimes what might happen is we just had, let's say, an alpha particle. We just had an alpha particle go in here. We just got this to be ionized, and we currently have a surge of current going through, a surge of charge going through our circuit. But maybe another alpha particle enters before that charge has got the whole way around to the counter. And it ionizes another set of particles, with the positive going towards the negative and the negative going towards the positive. But because that first surge of charge hasn't went the whole way around the circuit yet to get counted, that second charge will never get recorded. That second ionization will never get recorded because the first charge hasn't went through yet. So the dead time is that if another alpha particle, or another alpha, or another source, another radiation, so if another alpha particle causes ionization before the first is detected as a count. Sorry. Is not recorded. Okay, so that's why sometimes when we get our count rate, it's not actually equal to the activity of that source. So the count rate is what we get in our Geiger tube. The activity is how much radiation is given off. But clearly, the count rate might not always be equal to the activity because some of that activity, some of those ionization might not go recorded because of the dead time in our Geiger tube. Okay. Another thing to be aware of is, again, that we know that alpha is going to cause the most ionization, the most number of counts, then beta, then gamma. But again, we always have to be aware of how far away that source is from our Geiger tube. Because if our source is really far away from the Geiger tube and alpha only has a range of 5 centimeters in the air, none of it's going to get recorded, even though it's the most ionizing.